Lockheed Martin is having a tough year, losing out on new Air Force and Navy fighter contract opportunities in March, and then announcing $1.6 billion in quarter two losses in July.
America's most top secret spy plane isn't just for taking photographs anymore. The SR-72 will also drop hypersonic missiles.
For nearly 30 years, the question at the forefront of advanced aviation has been, what comes after the legendary SR-71 Blackbird? That aircraft, once the world's fastest and highest flying manned reconnaissance platform, pushed the boundaries of aeronautics and intelligence gathering to their limits. As successor plans to the Blackbird remained unclear, rivals and allies alike sought to gain the next leap in speed, stealth, and strategic reconnaissance. Now, the focus is firmly on the potential of a new era, signaled by the highly anticipated Lockheed Martin SR-72, introducing the SR-72 Darkstar, a conceptual hypersonic design projected to achieve speeds beyond Mach 6, integrating advanced propulsion innovations, next-generation stealth features, and enhanced artificial intelligence. Unlike any incremental upgrade, the intent behind the SR-72 is to transform the very principles of rapid aerial reconnaissance and intelligence collection. Respect for secrecy remains paramount, but discussion of the concept alone has already spurred debate among military experts worldwide. This emphasis on unprecedented speed, autonomy, and survivability reshapes expectations, not only for how quickly information can be obtained, but also for the viability of traditional air defenses. The SR-72's anticipated features compel rivals such as Russia and China to reassess established air defense strategies and resource allocation. Even as a concept, its possible capabilities have a tangible influence on the strategic calculus of other nations, providing a glimpse of what future technological competition in the skies might look like. Hypersonic flight, mastering Mach 6 and beyond. To understand why the SR-72 has captured so much attention, we must consider the physics and engineering challenges of hypersonic flight. Mach 6, a speed exceeding 4,600 miles per hour, presents a realm where only a handful of experimental vehicles have ventured. At these velocities, flight ceases to be a matter of conventional engineering and enters the world of real-time solutions to rapidly escalating temperatures, material stresses, and aerodynamic instabilities. The required materials for such flight must survive atmospheric friction that can increase skin temperatures to levels beyond the melting point of most conventional metals. Leading edges of the aircraft, in particular, bear the brunt of this heat, requiring specialized heat-resistant materials such as advanced ceramics, refractory alloys, and possibly carbon composite components. These considerations echo decades of lessons from earlier programs like the X-15, SR-71, and the Space Shuttle. Each made breakthroughs in materials science and cooling solutions that now inform new projects. Maintaining structural integrity and control at hypersonic speeds also presents major aerodynamic and systems challenges. Shockwaves form at the nose and along leading edges. Intense pressure fluctuations and aerodynamic instabilities must be managed without sacrificing maneuverability or endurance. Furthermore, friction with the atmosphere generates not just heat, but radio-opaque plasma that can disrupt communications and navigation. Aircraft like the SR-72, if realized, will depend on further refinements in both aerodynamic shaping and thermal management. Unlike previous hypersonic demonstrators, the vision for the SR-72 seeks to unite advanced speed with stealth, effectively minimizing the aircraft's contact with enemy sensors, both through rapid transit and specialized exterior shaping or coatings. This is not only a matter of flying fast, but of remaining untrackable during highly sensitive missions. Such developments prompt a significant question for national defense planners. How do you construct an effective defense against an object that nearly outruns both sensor networks and missile systems, and that may possess a drastically reduced radar cross-section? TBCC propulsion the twin-engine solution. At the center of the SR-72 concept lies the turbine-based combined cycle TBCC propulsion system. This approach addresses a long-standing challenge in hypersonic flight. No single engine type performs efficiently across the entire spectrum from takeoff through Mach 6 plus flight. Turbojets and turbofans excel at low to supersonic speeds, but lose effectiveness at higher velocities. Scramjets need the aircraft to already be moving at high speeds before they can operate efficiently. A TBCC system combines these two propulsion methods. At takeoff and subsonic speeds, a turbine engine powers the aircraft, functioning as in conventional jets. As the aircraft accelerates past Mach 2, airflow management systems transition the propulsion regime to a scramjet, in which air is compressed by speed and combusted at supersonic rates. The transition is a major technological challenge, demanding precise management of airflow, pressure, and temperature within the engine. This advanced approach would, in theory, enable a vehicle like the SR-72 to operate from standard runways. It could accelerate under its own power into the hypersonic regime, unlike rocket-powered vehicles that require special launch arrangements. The adaptability and repeatability of such a vehicle is of major strategic significance. It could support regular reconnaissance or intelligence-gathering missions at global range, rather than one-off experimental flights. The practical results of such a propulsion method are far-reaching. Flight profiles could include rapid sprints into denied airspace, fast turnarounds for follow-up missions, and possible long endurance for intelligence and surveillance tasks. By reducing logistical requirements like mid-air refueling or remote launches, the platform increases its operational flexibility and potential responsiveness. TBCC engines, if successful, could also support a broader array of mission profiles beyond intelligence gathering, including high-speed delivery of payloads deep into hostile territory. The major leap, however, remains in routine, sustainable, hypersonic operations, part of a gradual evolution toward future unmanned hypersonic strike and surveillance platforms. Stealth at hypersonic speed, shifting the detection challenge. Speed is only part of survivability. The SR-71 famously relied on its impressive altitude and velocity to evade interception by missiles and enemy aircraft, but it always remained detectable to radar. The SR-72 is envisioned to go a step further by attempting to minimize its signature in both radar and infrared spectrums, making it a more elusive target. Flying at altitudes above 88,000 feet, the SR-72 would exploit the upper margins of the stratosphere. At such heights, the air is thin, diminishing the threat from conventional anti-aircraft weapons and reducing aerodynamic drag, but it is also an environment that imposes extraordinary stresses on hardware and guidance systems. The fewer adversary platforms capable of reaching such altitudes, the harder it becomes to mount an effective response. Stealth technologies are anticipated to play a role, likely drawn from lessons learned during decades of development of platforms like the F-22, F-35, and B-2. Techniques may involve radar-absorbing materials, low reflectivity surface geometries, canted or blended edges, and internal bays for any required sensors or payloads. The aim is to scatter or absorb radar energy and reduce the chance of detection. Meanwhile, infrared signature management would be especially vital for an airframe operating at extremely high kinetic temperatures. The synergy of high speed and stealth complicates adversary detection networks. Even where tracking might be possible, the speed at which the SR-72 transits a given area allows minimal response time for ground or airborne defenses. Combined with electronic warfare countermeasures and AI-driven tactics, the net effect could be a platform that enters and exits hostile airspace faster than it can be reliably tracked or intercepted. Impacts on air defense, diminishing response windows. From a defense perspective, the prospect of a hypersonic reconnaissance platform challenges the very foundation of established air defense doctrine. Modern anti-aircraft systems, such as Russia's S-400 and S-500, or China's HQ-19 and HQ-9B, are designed for targets with more predictable speed and flight profiles. Their engagement windows and missile speeds, advanced as they are, may prove insufficient for reliably engaging a Mach 6+ platform flying at or above 88,000 feet. Furthermore, ground-based and airborne surveillance radars, even with phased array and frequency hopping capabilities, may struggle to achieve consistent, real-time tracking of such a fast and stealthy vehicle. The combination of minimal radar cross-section, unpredictable flight path, and extremely high speeds presents a formidable puzzle even for the most advanced sensor networks. The end result is a reduction in warning time, from potentially several minutes to mere seconds, and a corresponding increase in uncertainty for defenders. Resources must be spread thinner to protect larger areas, and the cost and complexity of maintaining an effective missile defense increases, all while the threat platform may only linger in sensor coverage for fleeting moments. The psychological factor, shaping adversary strategy. The mere possibility of a platform like the SR-72 imposes a new level of pressure on adversary planners. Even as a design concept with unproven operational history, its rumored capabilities exert a destabilizing influence on enemy decision-making and investment. The uncertainty requires adaptive new interception strategies, investments into emerging sensor technologies, and a reconsideration of established defensive doctrines. The existence, even in concept, of a hypersonic, stealthy, AI-enabled UAV is sufficient to generate shifts in priority. Potential adversaries may need to deploy more advanced over-the-horizon radars, expand space-based infrared detection networks, or invest in new kinds of responsive interceptor weapons, all at significant cost and with uncertain effectiveness. AI and autonomy, the machine at the controls. Hypersonic flight presents particular challenges for human pilots: extreme G-forces, rapid reaction times, and demanding environmental conditions far beyond the limits of human endurance. For these reasons, the SR-72 is anticipated to be crewless, relying on advanced artificial intelligence to manage flight controls, navigation, threat assessment, and real-time retasking. Autonomous systems are especially critical when split-second adjustments are required at hypersonic speeds. The AI integrated into the SR-72 would need to interpret streams of sensor data, predict and respond to potential interception attempts, re-optimize flight paths, and maintain mission priorities under dynamic and possibly contested electronic conditions. Such operational demands require continuous advances in algorithms, processing power, and system redundancy. Autonomy also means the aircraft can be optimized for performance, free from the mass and volume demands of a cockpit or life support systems, and tolerant of environmental extremes that would be prohibitive for human crew. The machine, thus, extends endurance and survivability, potentially venturing deeper into hazardous airspace and adapting faster to emerging mission needs. A persistent, unblinking platform that cannot be fatigued or demoralized becomes both a technical asset and a psychological one, promising reliable information gathering even in the face of contested environments. Strategic reconnaissance, the new art of knowing. The SR-72, if realized, is unlikely to focus solely or even primarily on strike roles. Rather, its most significant contribution may be to intelligence, surveillance, and reconnaissance (ISR) operations, missions rooted in the heritage of the SR-71. Effective ISR enables better situational awareness, more timely responses to developing threats, and enhanced deterrence. The promise of hypersonic speed is not simply the ability to outpace interception, but also to temporarily compress the intelligence loop. An unmanned aircraft capable of entering denied airspace, collecting high-quality imagery or electronic data, and returning all within an extremely tight window drastically narrows an adversary's confidence in their own ability to hide or reposition key strategic assets. Such a platform could, in principle, survey missile deployments, troops movements, or electronic emissions in near real time, acting as an instrument not merely of observation, but of persistent deterrence. This undermines the value of camouflage, deception, or delay in adversary planning, as well as allowing for the rapid confirmation of developing threats. Implications and the current status. Importantly, the SR-72 remains a concept as of 2025. No publicly acknowledged flight tests have occurred. The details of its design, specific operational systems, and service entry remain under discussion and speculation. Lockheed Martin has signaled a possible first flight by 2025, but such developmental timelines, especially at the edge of current technological capability, are characteristically fluid. Nevertheless, the plausibility and strategic implications of a hypersonic, stealth, unmanned reconnaissance platform are real. Already the concept shapes investment decisions in both the United States and rival countries. The increasing urgency on developing faster, higher-flying, more survivable ISR platforms reflects the knowledge that a credible hypersonic UAV could fundamentally reshape modern intelligence gathering. Competing nations are thus compelled to broaden their research into early warning technologies, space-based sensors, faster interceptor missiles, and new detection algorithms. National leaders and defense planners must prepare for a future in which traditional airspace boundaries and assumed warning times are rapidly rendered obsolete. The future geopolitical landscape. The SR-72, even in pre-flight status, serves as a forcing function for doctrinal reassessment. Every rumor or update from Lockheed Martin is scrutinized for hints of progress, compelling adversaries to keep pace in both technology acquisition and strategic preparation. The threat of a platform that can cross continents in under an hour and evade existing defenses acts as a strong form of diplomatic and military signaling, regardless of its current state of development. Such signaling extends beyond the technical. By influencing the budgeting, research, and doctrinal priorities of potential adversaries, the SR-72 project shapes not only the battlefield of tomorrow, but also the allocation of resources, attention, and innovation today. Rivals and allies alike are prompted to investigate quantum-enhanced sensors, hypersonic missile countermeasures, and new airspace management protocols. In many ways, the mere potential of the SR-72's capabilities, blending hypersonic speed, advanced stealth, and autonomous operations, becomes a weapon of influence, compelling shifts in enemy planning and ensuring that the technological edge remains with those willing to push the boundaries. Anticipating the SR-72, looking forward. The realities of modern great power competition mean that advancements in one country's aerospace technology are closely watched by all others. Every credible rumor, official announcement, or test footage leads to revised estimates of risk and reward among adversaries. Should the SR-72 fly as projected, the consequences would likely include the acceleration of hypersonic and counter-hypersonic technological races globally. The proliferation of corresponding detection and defense measures is both costly and technically challenging, but will be considered necessary in the face of a platform considered capable of negating existing air defense investments. At the same time, the adaptation and integration of AI, composite materials, and multi-regime propulsion could have downstream benefits for both military and civilian aerospace sectors, advancing the overall state of global aviation and spacecraft design. Conclusion. Redrawer of boundaries. Throughout aviation history, platforms like the SR-71 marked inflection points, moments when the assumed rules of what airpower could achieve were fundamentally rewritten. With the SR-72, Lockheed Martin aims for another such turning point, not merely to build a faster aircraft, but to upend assumptions about how quickly, quietly, and reliably intelligence can be gathered even in the world's most denied and contested spaces. As of 2025, the SR-72 remains untested in the skies, its details cloaked by national security requirements. yet the clarity of its strategic message is unmistakable. Potential adversaries must reckon with an approaching future in which hypersonic, stealthy, AI-driven platforms transform the risk calculus for any act requiring operational secrecy or surprise. For now, perhaps the most significant impact of the SR-72 is not on the battlefield, but in the boardrooms and ministries of defense where future battles are planned. Sensing the shifting balance, all powers are pressed to reconsider how and how quickly they detect, interpret, and respond to the rapid approach of next-generation capabilities. If or when the SR-72 Darkstar takes to the skies, it will not only redefine what is possible in aerial reconnaissance and deterrence, it will mark the next great leap in the long contest to control the high ground above. This is the new frontier, where hypersonic speed, adaptive stealth, and full autonomy combine, not just to challenge legacy defenses, but to reset the imagination of what superior air power can truly achieve.